thing about dynamic types is it's a bit, well, types in general, it's a bit weird to talk about in a dynamic language symposium because types are static, right? If you think about Smalltalk, you might have instance of and type of, but what you ask is a class, and that class is something that sits in the system dictionary. It's static. CLOS, multi-methods have got specializers, but those specializers are set up when your program runs. Functional language pattern matching, that's really static. You've got to define your GADT or whatever it is that you match against. And even gradual types, which are often kind of type systems we talk about here, at some point they're fundamentally static too, because the idea behind gradual types is, of course, you can do a static checker. But especially here in the DLS, what do we know about static stuff? It's boring. Wouldn't it? And so what we're going to talk about today are these first-class dynamic types, which perhaps are a way of thinking about types in a really dynamic language that's a little less boring. Work primarily done by Michael Homer, my colleague, and he doesn't like traveling, so that's why I'm here to talk to it. At this point, right. So, this is done in the programming language Grace that we've been working on for longer than I ever thought we would. One of the features of Grace is it has this notion of a pattern. It's a fairly general notion. If you're familiar with Ruby patterns, it's not that far off from that. You can use a pattern in an if statement like we're doing here. If the negative pattern matches some object, I guess it means it's a negative number, then we can do something. If it doesn't, we do something else. Oops, now I'm confused about which way this thing goes. Sorry. More useful is in something like a case statement, and this is Grace's match case statement, where we have a number of branches of the case, and for each one of these things here we're testing whether these particular patterns match the object that we passed in. And the interesting feature of Grace is that these things here, which are Grace blocks, they are effectively very similar to Smalltalk blocks or lambda expressions, with a syntax we quite like. Blocks are partial functions, so the way this works is a lambda can be, you can ask, when you pass in an object, does it actually match the pattern we've got here? If it does, it runs. If it's not, it says no, and then carries on. And traditionally in Grace, or at least the way we sort of thought of it, these things were supposed to be static, but it turns out in almost every implementation of Grace, we never really put the checks in, or if we did put the checks in to bind these things statically, you can pull them out and bind them dynamically. And that's really what this talk is about. What happens when you take the idea of something that looks like a static type, but say, well, we're the dynamic language symposium, let's do this dynamically. And I keep forgetting which button to press. Here is an implementation of the negative pattern, and these things are behaving like types. But, you know, this is just saying if something's negative. It's an if statement in here. Pretty much, it says if it's less than 0, then we return a successful match, and otherwise we return a failed match. What a successful match and failed match? Well, Grace is structurally typed, so they're actually objects that conform to Boolean. You can use them anywhere you would want to use a Boolean truth value. The difference is they're carrying on this extra object. In this case, it was the object you passed in. So if it's a successful match, we've got a successful match, and we know that this is the object that we matched, and then we can use that to inject into the lambda expression or whatever else we're doing. Here's an example we might want to use. So this is a half pattern. This actually matches any number. We're saying if number.match, there we are using the number match. If it is, then we're going to return successful match of the object divided by 2. Why would you want to do this? Well, because it's the kind of thing you can do dynamically, or because it will confuse people. I don't really mind, but you can do it, and if you put it in a program, you could have something like this, match 8, catch 8. What's this going to print? It's going to print 4. Why? Well, because this object came in and it matches 8, transforms it, and returns half. And I'm going to say the interesting thing about this code is, other than the number and the successful match and the failed match stuff here, we like to think this is pretty straightforward code. That's another part of the Grace shtick. It's to see how far can we get without going to metaprogramming. How far can we get without having to go to macros. In some cases, if you want to do stuff and have examples, you have to go to macros. But a lot of this stuff, we think of types as being special things. And this is kind of saying, well, actually, you can think about them as predicates over values, and you can write them as if they're predicates over values without necessarily having to invoke Gregor Kixavis, which is always worrying, I think, when you have to do that. Types in Grace, well, actually they already work as patterns, and in some sense that's how the Grace structural type system is implemented in our interpreters. Grace is a structural type. We've got a type with a method X and a method Y. One of the other theories about Grace is that everybody in this room should be able to read it without it being explained. Let me know afterwards if you can't. And so this object also supports that match interface. The twist that we take is effectively to say, well, we will generalize these patterns, the space of types in the programs so we can put these general dynamic patterns in. So here's a method declaration, and you can see there's parameters and return types. Those things can be annotated with these patterns or the type declarations. Field declarations, variables, constants, all of the kind of places you would expect to find a type in your program, you can put them in, and doing it this way, you can basically put in some kind of generic dynamic predicate. So what sort of stuff can we do? Oh, sorry, how does this work? First up, it basically works doing the obvious thing. This slide shows it using just a code-to-code translation. We don't, well, some interpreters do it this way, most of them just do the obvious thing. Effectively, first of all, we look up the pattern in Grace, like in Newspeak, or in Scheme, there's just a single lookup rule and a single namespace that's used for absolutely everything. I think that's great, and that's one of the other reasons why this kind of crossing over between types and values works. So we look it up and we bind it to a name. We then ask that pattern to match, and we get to match result. And then if the result matches, sorry, if it doesn't match, we report a type error. And if it did, well, then we return the value that was in that match result object. And that's basically it. Return values, it's essentially the same thing. We, again, find the return pattern, get the match result. And at this point, I'm going to throw my clicker over the room, and then we return it. So, what kind of stuff can we do? So if we want to, we can actually use this to replicate the standard structural types in Grace. Probably not there. Why would you want to do this? I don't know, but you can. Here we basically say, look, here's a method greet, and the object that goes in here has to have methods first name and last name, and then we can use that to print that stuff out. How do you implement a pattern to do that? Well, here it is. Okay, I said you weren't going to be reflection, but if you actually want to look at the objects, then you have to be reflection. So here what we do is we simply say we're going to use Grace reflection. We're going to look at the method names in the object. And if the mirror responds to that, if it doesn't respond, then we say it's failed. And if we go through all the methods in our type and have got an object that returns them, we return the successful match. The advantage of doing this, of course, is that if you run a program with one of these kind of types, you'll get an error saying you passed in a person, but this person doesn't actually have a first name. You'll get that when the greeting message is called, not from somewhere deep inside the body of the code when it actually tries to extract the fields and print the greeting. If we want to, we could say, we want an object that for some reason only exactly has those two methods. We can do that as well. In this case, we'll just do it by inheriting from the methods pattern from the previous slide. And then what we do is, well, we'll still do the reflection. And we say, look, is the mirror the same size as the size of the list of the patterns we want? If it's not, then we give up. And if it is, well, effectively, we invoke match methods, which was the match from the previous slide that we've inherited. So this is actually doing reasonably scary reflexive stuff, but the code hopefully is not too horrible. But what else can we do? Nominal brand types. Grace is structurally typed, but you all know this thing where you have a graphic object where draw means draw and a gunslinger. Which one is it? Do you really want your programs to confuse these kind of two? If you commit to structural types, then they will. Well, in Grace and in Wyvern and various languages have solutions to this that you say the language, and originally, of course, coming from Luca's Modular 3, where we say we want these structural type language for the formal properties. But when it actually matters, if we're using types as part of our analysis or part of our design, we can stick what are called brands, which are explicit types, onto those objects. We had a paper at eCoop about this, or Tim did a few years ago. We can implement that using this extension. So what we have to do is, okay, we've got the brand in Grace, classes and constructors. You don't use new, you just call it because there's only one namespace. This says we're going to make a new brand. Okay? So at this point, the brand is just an object. We're going to make a new object, and then what we do is we're going to tell the brand to brand that object with the information from the brand. Okay? And this is essentially an object capability thing because, well, in order to be able to brand something with this particular brand, that brand has identity, you actually have to have that particular brand object to be able to do a call like that and then brand an object. So you can control who is allowed to mark objects with any particular type simply by controlling the access to that brand. Then if we want to, okay, we can write a method like this, which says foo, and it takes an object, and the type of this is myBrand.type. Okay? So the brand is the thing that actually brands the object, and each brand has an associated type, which is a different object, which is one of these patterns, and so we can stick the type in here, and then it will do a check, and you'll only be able to get X into the body of foo if it in fact has that brand type. If we call this on a branded object, then that will work. If we call it on some object that doesn't have the brand, then it won't. How do we implement this? Well, basically the brand itself is pretty simple. It's more or less just an object. Okay, there's a bit of reflexive magic in here. When we actually want to brand an object with this brand, at this point we're sticking it into the object metadata. We probably could just have a large set of all the objects that's been branded, probably a bit quicker. And then for type, well, we say we're going to return one of these patterns. What does the pattern look like? Well, the pattern basically says, get the brand out of the object metadata, and if it's the same as the brand we first thought of, which has been passed in here, then we say this object has that brand, and if it isn't, we don't. Types. You can do more things than just types. Anyone start with Pascal? Yeah, old people. Pascal had subrange types, which is really cool. Viet, yes, you can call him, what's the line? You can call him by his name, which is Viet, or you can call him by value, which is worth. Sorry. Work that one out later. His language had subrange types. So for example, if UTF-8 characters, Unicode characters had been invented in 1970, when Viet was designing Pascal, you could say, I want a variable to hold one UTF-8 character by saying the range of that variable has to be between 0 and 114,112, because that's the range of Unicode characters. So if you have a declaration like this on a method, it will take some number that sits in that range, and if it is, it will let it in, and if it won't, it won't. Well, if it was rejected, you get a type error, dynamic type error. More usefully, perhaps, we could say, okay, Grace just has this one big class called number. That's from the educational heritage that we didn't want to have to start teaching people in the first week that in order to call different library routines, you had to understand what the difference between an integer and a floating point number was, because at least in New Zealand, most normal humans don't understand that distinction. So we just have this one big number type, but maybe we want a byte. Well, we can do this by saying, okay, we'll make a range between 0 and 255, and that'll be the byte, and yeah, we can have a method that prints it out. In fact, and if you like Pascal, you'll love this, Grace uses the double dot here to actually define a range. So we can actually write 0 to 100 like that, and if we want to, what we've done is we can overload that range object, which is just another Grace object, just comes out of the library. We put a definition for match onto that object. We can actually stick the ranges in here, and then we get the behavior you might think. How hard is it to write the actual match method? Well, it's not. In some ways, that's the idea behind Grace. We get to give a lot of talks, and we get to say, well, it's not a lot. You know, we take it as an object, and then we ask if the thing is in the range. That's basically all there is to it. If you like subranges, you probably love enumerated types. So, for example, again, slightly different syntax to Pascal, but we want to say here's a variable that can hold red, yellow, blue, or green. So we can make a set, a standard Grace set that has these kind of things, and then we actually wrap that set in a little adapter. We haven't overridden all the collections to say, okay, here's a type that will work if the thing is an element of that set. And so we can define Lego color as an element pattern of that, and then we can say, okay, here this is finding a brick, it's only supposed to take Lego colors. We say this, if you pass in something that's not a Lego color, you will get an error when this message gets called saying, oops, I've passed in the wrong kind of thing. If we want to, we can start getting, you know, more Haskell-y or Matrices. Matrices, we can say, okay, the matrix multiplication, well, it takes another, and it has to be the same width, and it can have any height, and, sorry, height and width. The height of the other matrix has to be our width, and the resulting matrix will have a height, which is our height, and a width, which is the other width. How do we do this? Well, once again, it's not hard. We just basically say these things we take in as patterns, and then we say, okay, do these things match? If they do, we succeed. If we don't, they fail. What else? Argument-dependent patterns. The X10 language has these kind of constraint types where you can basically say, well, in this case, we want to take an X in, and we want to take a Y, and we want to say the Y is larger than X. So with a little bit of trickery that I'll demonstrate, you can actually do it and let you write something like this. X has got to come in Y, and Y has to be greater than X. Or, we can say we want to get something out of a list, and we get the list, and, the index has to be greater than 0, and it has to be less than or equal to the list size. So we can, and then if it is, we go ahead and get that. How do we do that? Well, this is a bit sneaky, and in some ways this shows the Smalltalk heritage, which is lurking just below Grace's syntax. I don't want to say Andrew Black's involved in this program. We took a lot of Smalltalk and we tried to make it so it would be readable. My favorite Luca Cardelli joke is when asked what he would change about modular 3, he said, I wish I'd used curly brackets. So Grace, in some ways, there's a lot of Smalltalk there, but we used curly brackets. So, okay, first of all, we have this notion of we're going to make a notion of a relative pattern, which takes in a lambda expression. That's one of those blocks. And what we're going to say is, well, basically, we'll apply the lambda to the object we're matching against, and if it's successful, we'll succeed. If it's not, we'll fail. So this is basically a wrapper that lifts a Boolean predicate up to the successful match, failed match thing. And then what we do is we define an object called B. And this object called B has a bunch of methods on it, which implement all these comparison operators. And the way you implement the comparison operator is we have this predicate that we're lifting, and then we stick it in here as a pattern. So that means if you send the message less than to this object B, what you get back is a pattern, and then what that pattern will do is it will apply that same operator to the object that you're matching against. And that's how we can say something has to be less than 7 or something has to be within the size of the list, just by routing these things through here. Oh yes, anyone love C++? Excellent. There's 3 people in the dynamic. There are 3 people in the dynamic language symposium who put their hand up when I asked if they love C++. It's only here, folks. It's only here. The thing about any language mechanism, any dynamic language mechanism, if you can do something interesting with it, you can do an awful lot of horrible things with it. So we can do things that the C++ people would have nightmares about. I mean, they have nightmares about what they're doing anyway, but we can have those nightmares too. So here's one, Stringify. Okay, it's kind of an odd thing, and it takes in a match, and it's always successful. It's an irrefutable pattern; it will always succeed. And what it does is it just converts the object to a string. So now, if you want to, you can write a method like foo, which is not going to print out very much interesting, but its argument is stringified. And what this means is it doesn't matter what you call foo with. You could call it with hello, you could call it with 1, you could call it with widget button.close. Anything you like will go in here, and as it goes through that pattern, it gets converted to a string, and so inside the body of this method, that argument there will always be bound to a string. So we can do conversions. We can get even further if we like. Var rating, look, it's iTunes, this number's got to be between 1 and 10. Well, we can define something like this, clamped between 1 and 10, and then, it looks like a variable declaration, and we're assigning 999 to it. How can that work? Well, if we print out the rating, it's going to print 10. Why? Well, once again, because we're using the abilities of these patterns to change the object that's passed through. I'm not supposed to say mono. Who would want to anyway? Basically, again, class clamp between those two, what happens? Well, it's the obvious code. If the object is less than the minimum, then we pass in the minimum. We return the minimum as a successful match. If it's greater, we return the maximum. And otherwise, Well, gee, it's just a successful match. So you can basically kind of do all sorts of horrible stuff with this. Eiffel invariance, I think this one is actually pushing the boat out a bit far. Okay, we've got a class rabbit in some game, it's got some hit points and some maximum number of hit points, and we can define an invariant, well in this case it's a confirm pattern, which takes a predicate and effectively we're going to say this invariant has got to confirm that the number of hit points is less than or equal to the number of max hit points. Yep. And you know, we can have methods, and if we want to have that in, as a post condition, that invariant, we can just write it in as part of the return type. Okay? What this means is that every method where you see that, if you want it, I guess it's a precondition, you can stick this on the types of at least one of the arguments going in, or you can assert it at the top of the method, I guess. And that means that this invariant will be checked. How does that do it? Well, in some ways it's a bit like the opposite of the patterns that we've just been looking at, which would always succeed and do something to the value. What this does is we just ignore the value. Okay? Basically, we ignore the value, we apply the predicate. If it succeeds, we say we've succeeded with the object was passed in, and if that predicate fails, we say we fail with the object is passed in, but we never actually look at the object, and we don't even have to do that in the syntax of anything that we put into one of these confirmed types. Decorators. Okay, this one's a little bit weird, and I guess this goes out to Bev and the racketeers sitting in the corner. This type here, the idea is this will be a list of string. Actually, there's a class very much like this in the Java Sound library. It does something very similar. What are we going to do? Well, it's one of these patterns. When will it match? Well, first of all, we ask, is this a list? So that is list. That's, in this case, that will presumably be bound to the standard language structural type list. It says, is this as a list? And if it's not a list, then whoops. That's right, we can return the match result because the match result behaves like a Boolean, so we can test it here and then return it. But if it is a list, what we're actually going to do is we're going to decorate it with a decorator, and then we return that object as part of the successful match. So this is another one of these patterns that's transforming the object that flows through it. What's the decorator? Well, the decorator is pretty simple. It just says if you've got an add method, then you'd better pass in a string. If you've got a get method, you'd better return a string. And if you set something, then the value you're setting had better be a string. Okay? And that then means, you know, this is providing more type checks, more gradual type checks around a view of a particular object. So, you know, we can do stuff like this. Oh, we'll initialize a string list with 1, 2, 3. Okay, is this going to work?
Yeah.
Yeah? Why is it going to work?
Because it's a list?
This will in fact work because that, if you remember the pattern on the previous slide, it says, is this a list? So it's doing a shallow check, a first order check. It just so happens that this list has already got stuff shoved into it. Not ideal, but we're dynamic people, we can cope. Might not be able to cope with this, but I can cope with that. If we add something to it, if we add a string to it, that'll be fine. If we add a number, then that won't be fine because this will be caught on the type test going in. And if we ask, well, at 1, in this case, that will also fail because presumably the first thing in the list is the number 1. I guess if we've done this and then we ask for the fourth thing, presumably we would get the hello string out and that would all be okay. Whether this is a good idea or not, I'm going to say, but we're flexible enough to do it. So, since my time is running out, related work, well, there's actually, you know, RTFP basically. There are lots of object-oriented languages, some static, some dynamic, that are growing various types of pattern matching system that can do some or most of this. What generally they don't do is let you put things into the types. Already talked about the functional language. F# has active patterns. E has guards. If you get hardcore, there are various things you can do with meta-object protocols. You may well be able to redefine what it means to be a slot accessor and then do a type on that particular slot accessor by redefining stuff at the meta level. Part of the point of this, of course, is that I'm trying not to do stuff at the meta level unless I really, really need to. Big related work here is racket. So we define a racket procedure here called spy, which just displays the thing we pass into it and prints out the value. We can define a version of spy. Sorry, what's this? We can define a contract here. It's a racket contract. This is the closest equivalent to, well, I guess it's like a racket dynamic type. It's called add1c. It's going to ask if this thing is a number. And in fact, racket has an extra part of the contract called a projection, and in this case we're going to just have the function add 1 to something. All right? So if you define a version of spy with the contract on the argument and on the return value and the argument, the body of this is exactly the same as the body up here. It's displaying x and then returning x. What will it actually do? Well, if you do call this spy with 1, what it will actually do, of course, is print out 2, because this contract here runs and adds to it, and then it will actually return 3 because it adds another number. This is evil. In some sense, you could say, well, a lot of this talk has precisely been about stuff that you could do in Racket. And maybe it is, but they were never mad enough to give a talk about doing that in Racket. And the other thing, you know, again, being in WG 2.16 and looking at language design, syntax is important. The other thing that Racket doesn't have that we do is they've got to go define contract. Whether for good reasons or bad reasons, we put in syntax for allowing those sort of types in at the beginning of the language because we knew we wanted to do something gradually typed. We didn't necessarily know what. And that, I think, has led us to doing this work and coming up with ideas like this and the other stuff I've been talking about because sort of the syntax is there to support it. So to conclude, what I've talked about is how first-class patterns can become first-class types. I'm going to claim it's flexible and powerful and simple. What we have here are more dynamic types, and what they are is more fun. Thank you. Don't know where the more fun is. Thank you.